Let the room grow quiet now and imagine the soft darkness before dawn settling over the old Tuscan city of Pisa, the Arno moving slowly beneath its bridges, the narrow streets still cool from the night, the bells waiting in their towers, and beyond the walls the fields fading into a pale horizon in this world of stone houses, church courtyards, merchants, craftsmen, scholars, sailors, and musicians. A child was born on the 15th of February in the year 1564. His name was Galileo Galilei, and although later centuries would turn him into a symbol, a rebel, a hero, a warning, and sometimes even a legend larger than life, he began as a son in a family that knew both pride and uncertainty. His father, Vincenzo Galilei, belonged to an old Florentine line that had once possessed greater wealth. Yet by Galileo's childhood, the family lived with modest means, depending on skill, reputation, careful arrangements, and persistent work. Vincenzo was a gifted lutenist, a composer, and a restless thinker about music. He questioned inherited rules, tested intervals with strings and weights, and argued that tradition should answer to experience. His way of listening to nature would leave a deep mark on his eldest son, not because Galileo simply copied his father, but because he grew up in a household where an established authority could be respected and still examined, where harmony could be discussed through number, where a beautiful sound might also be a measurable event, and where a confident claim invited the quiet question of whether it was truly so. Galileo's mother, Giulia Ammannati, came from a family connected with the cloth trade. She managed the household through years of movement and financial strain, and the young Galileo would later inherit obligations toward his brothers and sisters that weighed upon him as heavily as any stone in one of his mechanical studies. The family moved to Florence when he was still a boy, leaving Pisa for the city of the Medici, a place of workshops, painted chapels, busy markets, formal courts, and memories of artists who had joined geometry to vision. There Galileo learned not only from books, but from the visual order of Renaissance life, from perspective in painting, from buildings raised according to proportion, from machines used by artisans, and from music shaped by ratio and disciplined practice. For a time he studied with monks at Vallombrosa, a green and peaceful monastery in wooded hills east of Florence, and there he appears to have considered a religious vocation, perhaps drawn by the calm rhythm of prayer, learning, and communal life. But his father brought him home, preferring another path, and the future observer of the heavens returned from the forested silence to the complicated demands of family ambition. When Galileo reached the age for higher study, medicine seemed a sensible profession, respected, practical, and capable of supporting a family. So in 1581 he entered the University of Pisa, where students heard lectures rooted in the works of Aristotle, Galen, and their commentators. Medieval universities did not merely repeat ancient words without thought, yet authority carried enormous weight, and knowledge was often organized through careful reading of revered texts. Medicine required philosophy, logic, anatomy, and an understanding of the qualities believed to govern the body. But Galileo's attention wandered toward mathematics. The change was not a sudden magical awakening beneath a lamp, nor was it caused by one perfect moment. It developed as he encountered geometry and the mathematical tradition associated with Euclid and Archimedes. One important guide was Ostilio Ricci, a mathematician linked to the Tuscan court, whose teaching offered Galileo a different kind of certainty. A geometrical proof did not depend on social rank. A diagram could compel the mind step by step, and the balance of a body could be understood through relations that remained true whether a professor approved of them or not. Galileo began to see mathematical reasoning as a key to physical questions, though at this early stage the connection between abstract demonstration and the changing world of matter was still difficult and unfinished. His father worried that mathematics promised less income than medicine, and that concern was reasonable. Yet Galileo left the university without taking a medical degree, choosing a path that offered intellectual excitement but no secure position. He supported himself through tutoring in Florence and Siena, cultivated patrons, wrote on the center of gravity of solids, and developed a hydrostatic balance inspired by Archimedes. The balance allowed an object to be weighed in air and in water, so that differences in apparent weight could reveal something about composition. It was an instrument, a calculation, and a performance of intelligence, exactly the combination that would characterize much of Galileo's life. Around these years later, storytellers placed one of the most famous scenes associated with him: the young student watching a lamp swing in Pisa Cathedral and comparing its motion with his pulse. The image is gentle and memorable, a hanging lamp moving through ever smaller arcs, while the interval of each swing appears nearly unchanged. It captures Galileo's attention to ordinary movement, yet the precise story cannot be accepted as a simple eyewitness record. What matters more is that pendulums did become part of his long investigation of motion, and that he learned to notice time within movement itself, not merely the beginning and the end. He considered how repeated swings might measure pulse or regulate time. Though the fully practical pendulum clock would belong to a later generation, the tale survives because it expresses something true about his habits. He could look at a familiar event and ask a question that others had not framed in the same way. He could turn the commonplace into a problem, then the problem into a measurement, then the measurement into an argument, and still remain dissatisfied until the argument had been sharpened. In 1589, Galileo received a position teaching mathematics at Pisa. Helped by the support of influential mathematicians including Guidobaldo del Monte, the appointment brought him back to the university, where he had once been an uncertain medical student. Now he lectured on geometry, astronomy, and the mathematical subjects expected from his chair. His salary was limited, his responsibilities were real, and his temperament was not naturally suited to silent conformity. Later tradition imagined him dropping 2 balls from the Leaning Tower of Pisa before an astonished crowd, proving in a single theatrical gesture that heavy bodies and light bodies fall together. The episode may contain echoes of real demonstrations, but there is no secure contemporary account that allows us to describe it as established fact. Galileo did challenge important Aristotelian claims about falling bodies, yet his development was gradual, involving thought, calculation, observation, inclined surfaces, and debate, not one triumphant afternoon beneath the tower. In manuscripts often connected with his early work on motion, he explored how bodies descend through a medium, how density affects motion, and why the standard explanations seemed inadequate. At first, some of his own ideas remained entangled with older physics, as new thinking usually remains entangled with the language it is trying to escape. He did not awaken fully modern while everyone around him slept in error. He advanced by revising, contradicting, testing, and sometimes abandoning his earlier positions. The ancient view commonly taught in his world described natural places and natural motions. Heavy earthly matter tended downward toward the center of the universe. Lighter elements moved upward. Heavenly bodies belonged to a different region and moved in perfect circles. Within that system, motion was not merely a change of position. It expressed the kind of thing a body was and the order of the cosmos. Galileo increasingly approached motion through quantity, asking how distance, time, speed, and acceleration were related. This shift sounds simple, after centuries of physics have made such questions familiar, but it required a profound change in attention. Instead of asking only why a stone sought the center, one could ask how its speed changed during descent. Instead of accepting that a heavier stone must fall in direct proportion to its greater weight, one could imagine 2 stones tied together and notice that the traditional rule created a contradiction. If the lighter stone slowed the heavier one, the combined body should fall more slowly than the heavy stone alone. Yet as a combined body, it would also be heavier and therefore should fall faster. Such reasoning did not by itself supply every law of falling motion, but it cleared space for another account. Galileo's Pisa years were brief. In 1591, his father died. leaving him with financial duties toward the family, marriage portions for sisters, support for relatives, and expectations that a professor's income could barely meet. University life also offered limited freedom and advancement. So when a better opportunity appeared in Padua, within the Venetian Republic, Galileo pursued it. In 1592, he accepted the chair of mathematics at the University of Padua, and the move opened what he would later remember as some of the happiest and most productive years of his life. Padua stood within a republic whose commercial energy, printing culture, maritime power, and political independence created a distinctive atmosphere. Venice ruled the region, merchants crossed seas, shipbuilders worked in the arsenal. Physicians taught anatomy, diplomats gathered news, and practical mathematics mattered for fortification. Artillery, navigation, surveying, and trade. Galileo lectured to students from many lands, trained private pupils, advised on technical problems, designed instruments, and built a household where intellectual work and craft production were closely joined. His official lectures still included the astronomy of Ptolemy, whose Earth-centered system allowed the positions of planets to be calculated through a sophisticated geometry of circles. He also taught Euclid, mechanics, and military architecture. But outside the formal course, he pursued questions that would eventually transform his reputation. He did not work alone in an empty chamber. Artisans ground metal, glassmakers shaped lenses, assistants copied diagrams, students discussed results, patrons requested devices, friends carried letters, printers prepared pages, and mathematicians across Europe exchanged claims and criticisms. The familiar image of the solitary genius contains part of the truth. For Galileo possessed unusual intensity and confidence, yet his achievements grew within networks of labor and conversation. At Padua, he operated a workshop that produced a calculating device often called the geometric and military compass, or sector. Its hinged arms carried scales useful for solving many practical problems. Soldiers could calculate artillery charges, engineers could find proportions, merchants could perform conversions, and geometric operations could be made through the movement of the instrument. Galileo sold the device, offered lessons in its use, and published an instruction manual. He also became involved in a dispute with Baldassare Capra, who issued a Latin work that appeared to appropriate the instrument. Galileo responded fiercely, gathering evidence and defending his authorship before university authorities. The episode revealed a world in which invention, publication, prestige, and livelihood could not be separated. Padua also gave Galileo access to the Venetian elite. Among his friends was the statesman and theologian Paolo Sarpi, a learned Servite friar whose intelligence and political courage made him one of the striking figures of the Republic. Galileo knew Gianfrancesco Sagredo, a witty Venetian nobleman whose name would later become that of a character in the dialogue. He corresponded with scholars and sought the support of patrons able to protect a mathematician whose expenses always seemed to expand. He taught young aristocrats who paid privately for instruction. He hosted visitors, and he gained a reputation as a brilliant conversationalist, sharp, entertaining, combative, capable of turning a technical issue into a vivid contest of minds. His prose would later carry this spoken energy, moving with examples, jokes, analogies, and carefully staged objections. He understood that ideas travel not only because they are true, but because they are made memorable. During his Padua years, Galileo formed a relationship with Marina Gamba, a woman from Venice. They never married, but they had 3 children. Virginia in 1600, Livia in 1601, and Vincenzo in 1606. The arrangements of their household remain partly hidden by time. Yet the children became central to Galileo's private responsibilities. His daughters, born outside marriage, faced limited prospects in a society governed by status and dowry, and Galileo eventually placed them in the convent of San Matteo at Arcetri. Virginia became Sister Maria Celeste, Livia became Sister Arcangela, and their enclosed lives would intersect differently with their father's later years. Vincenzo was eventually legitimized and entered adult life outside the convent walls. These family decisions can appear severe from a modern distance, and they were shaped by social structures, money, reputation, and the narrow choices available to women, the letters of Maria Celeste, preserved while Galileo's replies are lost, reveal affection, worry, practical exchange, and a daughter's steady care for a famous father who still needed food, medicine, mended linen and prayer before the telescope brought the heavens close. Galileo spent years thinking about earthly motion. He explored the path of projectiles, the behavior of pendulums, the strength of materials, and the descent of bodies. Measuring fast fall directly was difficult because available clocks were crude and human reaction slow. One elegant solution was to reduce the speed by using an inclined plane. A ball rolling down a gentle slope could display the structure of accelerated motion in a form that allowed intervals to be compared. Water flowing from a vessel could serve as a measure of elapsed time. Distances could be marked, repeated trials could reveal regularity. Historians continue to study exactly when particular experiments occurred and how Galileo joined idealized mathematics with physical procedures. But his mature result was clear. In uniformly accelerated fall, the distances traveled from rest grow in proportion to the squares of the times, and equal successive intervals of time correspond to increasing distances according to an odd number pattern. The law transformed falling from a vague tendency into a mathematically ordered process. It did not require perfect vacuum chambers or modern electronic sensors. It required an ability to design a manageable situation in which nature's pattern became legible. He also developed a principle resembling inertia, though not yet the later Newtonian law in its final form. Imagine a ball descending one inclined plane and rising on another. The lower it falls, the more speed it gains. And on the opposite side, it tends to recover the height from which it began. If the second slope becomes gentler, the ball must travel farther to reach that height. And if the receiving surface becomes horizontal, it would continue without finding the rise that would bring it to rest. Friction and resistance obscure this persistence in ordinary life, but thought can separate the ideal motion from the disturbances surrounding it. This style of reasoning became one of Galileo's great tools. He did not merely record whatever happened in a complicated setting. He imagined limiting cases, removed accidental effects in the mind, and asked what relation would remain under purified conditions. The result was not fantasy detached from experience. It was a disciplined way of discovering order beneath friction, roughness, wind, and imperfection. In the final years of the 16th century, the old European cosmos was already under strain. Nicholas Copernicus had published a sun-centered arrangement in 1543, proposing that Earth rotates daily and travels yearly around the Sun. The book offered mathematical advantages and revived ideas with ancient precedents, yet it did not instantly overturn astronomy. Many readers treated it as a calculating hypothesis. Others objected that a moving Earth contradicted physics, common sense, and certain readings of Scripture. Tycho Brahe created an alternative in which the planets orbited the Sun while the Sun orbited a stationary Earth. Preserving much observational success without giving Earth motion, Johannes Kepler, using Tycho's observations, would argue that planets travel in ellipses, but Galileo never embraced Kepler's ellipses, retaining a deep preference for circular motion. The scientific revolution was therefore not one clean march by a united modern camp. It was a field of competing models, partial insights, inherited commitments, new instruments, and personalities who agreed on one question while disagreeing sharply on another. Galileo seems to have accepted Copernicanism privately by the late 1590s. He wrote to Kepler in 1597 that he had long held the view and had found it useful in explaining natural effects, yet he hesitated to declare himself openly, remembering how Copernicus had been mocked. The evidence then available did not force every observer to grant Earth's motion. No annual stellar parallax had been detected. Objects did not appear to be flung from a rotating globe, and the physics required to explain why birds, clouds, and falling stones share Earth's movement was still developing. Galileo would help make that physics conceivable, but before 1609 his public standing rested mainly on mathematics, instruments teaching, and the promise of work not yet fully published. Then news arrived from the north of a tube with lenses that made distant objects appear near, and the quiet preparation of years suddenly met an instrument that could turn hidden light into public wonder. The first spyglass was not Galileo's invention. Reports of such a device reached Venice in 1609 from the Low Countries, where spectacle makers had combined lenses so that distant church towers, ships and people appeared enlarged. Galileo heard the principle rather than receiving a finished instrument, and with practical knowledge of optics and access to Venetian glass, he began making his own versions. At first the magnification was modest, then he improved the shape, placement, and alignment of the lenses until the tube became far more powerful. The process demanded skilled hands as well as mathematical understanding. Bubbles or irregularities in glass could blur the view. The field was narrow, the image trembled, and focusing required patience. Yet for a maritime republic, even an imperfect telescope promised advantage. An approaching fleet could be recognized before unaided eyes saw more than a haze. Merchants could identify ships sooner, and commanders could study distant fortifications. Galileo presented an instrument to Venetian leaders from the height of the Campanile of San Marco, allowing them to look across the lagoon and see objects that seemed suddenly brought near. The demonstration was a success, his salary was increased, and his appointment strengthened, though the reward also carried an obligation that made his position less flexible. For a courtly scholar, every gift was part of a relationship. What followed changed the telescope from a military curiosity into an instrument of natural philosophy. Galileo turned it upward, perhaps first toward the moon, then toward stars and planets, and the sky that appeared through the tube was not the calm, polished ceiling described by simple textbook diagrams. The moon's boundary between light and dark was rough. Broken and irregular, bright points appeared within the shadow. Dark pockets entered the illuminated region, and these shifting patterns suggested mountains, valleys, hollows, and elevated peaks catching sunlight before lower ground. By comparing the geometry of light and shadow, Galileo estimated lunar heights, treating the moon as a world with landscape rather than a perfect smooth sphere made of unchanging celestial substance. Artists trained in perspective could understand the force of his drawings because they recognized how shade reveals form. Galileo's visual culture mattered here. He knew that an image was not merely decoration. It could become an argument. He turned toward the Milky Way, that pale band long visible across dark skies, and found it resolved into a crowd of stars too faint and numerous for the naked eye. Other cloudy patches likewise opened into clusters. The fixed stars did not become large disks in the way planets appeared, a difference that would later matter in debates about their distance and size. The telescope multiplied the population of the heavens, showing that ordinary sight had never displayed the whole visible universe. Even where no special object seemed present, more stars waited, and this discovery carried a quiet philosophical weight. The senses were not useless, but they could be extended, corrected, and trained through an instrument. Nature contained more than immediate appearance disclosed. Then in January 1610, Galileo observed Jupiter and noticed small bright points near it. At first he thought they were fixed stars, but night after night their positions changed, sometimes arranged on one side, sometimes divided across the planet. Sometimes fewer were visible because one passed behind or before Jupiter. After repeated observations, he concluded that 4 bodies revolved around Jupiter, a miniature system traveling through the sky. The discovery did not alone prove that Earth moved around the Sun, but it destroyed the claim that every celestial motion must be centered on Earth. An object could orbit a moving center, and if Jupiter carried moons while itself circling elsewhere, then Earth might carry its own moon while traveling around the Sun. Galileo understood both the intellectual and political value of the discovery. He named the bodies the Medicean stars in honor of Cosimo II de' Medici and the ruling Tuscan family. The name transformed celestial novelty into courtly tribute, placing the Medici symbolically in the heavens while presenting Galileo as the discoverer able to offer such a gift. He rushed his observations into a short Latin book, Sidereus Nuncius, commonly translated as the Starry Messenger. Printed in Venice in March 1610, its pages announced the rough moon, innumerable stars, and Jupiter's satellites with a speed that helped secure priority. The book spread across Europe and made Galileo famous. Readers argued over the reliability of the telescope. Some struggled to see through poor instruments, some suspected optical deception. Some accepted one discovery and resisted another, and some critics found that the heavens had become politically inconvenient. A tube, built by a craftsman and interpreted by a mathematician, now challenged distinctions embedded in philosophy and education. Yet the response was not simply old men refusing to look. Telescopes varied greatly in quality. Viewing required practice. Internal reflections produced false lights, and a responsible observer had reason to ask whether the image represented an external body or an artifact of lenses. Galileo had to establish not only what he saw, but why telescopic sight deserved trust. Johannes Kepler in Prague responded warmly, publishing support even before he had a suitable telescope with which to confirm every detail. Kepler's generosity mattered because he was one of Europe's leading astronomers. Though Galileo did not return equal enthusiasm for Kepler's most important discoveries about elliptical planetary paths, the relationship reminds us that great thinkers may recognize one another imperfectly. Kepler admired Galileo's celestial revelations and urged him forward, while Galileo remained largely silent about the ellipses that would become essential to modern astronomy, perhaps because his own physical imagination favored circles, perhaps because he disliked parts of Kepler's speculative style, perhaps because intellectual attention, like human attention everywhere, was selective. For Galileo, the fame of the Starry Messenger offered a route home to Tuscany. Padua had given him freedom, income, students, and access to Venice. But court service promised status beyond that of a university mathematician. The title he sought was carefully phrased. He wanted to be not only mathematician but philosopher to the Grand Duke, because natural philosophy stood above mathematics in the hierarchy of knowledge. Mathematicians calculated appearances, philosophers explained reality. Galileo intended to claim the right to speak about what the universe truly was. His naming of the Medicean stars supported negotiations, and in 1610 he accepted appointment as chief mathematician and philosopher to Cosimo. Along with a nominal position at Pisa that did not require routine teaching, he left the Venetian Republic for Florence, a decision that increased his prestige while removing some of the institutional protection and intellectual space he had enjoyed in Padua. At court he would have time to write, but he would also live closer to the shifting winds of patronage, reputation, and theological politics. Before and after the move, he continued to observe. Venus displayed a full sequence of phases, appearing sometimes crescent, sometimes broader, with changes in apparent size. This result contradicted the traditional Ptolemaic arrangement, in which Venus always remained between Earth and the Sun, and therefore could not show the complete range. The phases fit a system in which Venus circles the Sun, but they did not distinguish decisively between the Copernican system and Tycho Brahe's geo-heliocentric model. Both allowed Venus to orbit the Sun. The observation therefore weakened old Ptolemaic astronomy without proving every part of Copernicanism. Galileo's public rhetoric often pressed evidence strongly, yet the historical logic deserves calm precision. Celestial discoveries accumulated against one framework and made another more plausible. But alternatives remained. Saturn gave a stranger image. Galileo saw it as if accompanied by two smaller bodies, one on either side, and later the companions seemed to vanish. His telescope could not resolve the rings, so he described a triple form and remained puzzled when its appearance changed. The answer would await better optics and Christian Huygens, who interpreted the ring system decades later. This was a useful limit. Even a revolutionary instrument could present a truthful pattern that its observer could not yet explain. Discovery did not mean immediate comprehension. Sometimes nature arrived as a shape without a name. Galileo also watched dark markings move across the sun, today called sunspots. Observing the sun through a telescope required dangerous methods if done directly, and safer projection allowed its image to fall on a surface. Where spots could be traced over successive days, their movement suggested solar rotation, while their changes in shape and appearance challenged the doctrine of incorruptible heavens. Other observers studied sunspots too, including the Jesuit Christoph Scheiner, and a dispute developed over priority and interpretation. Scheiner at first proposed that the spots might be small bodies circling the sun rather than marks upon it, a view that preserved the sun's perfection. Galileo argued that they lay on or near the solar surface, altered, formed, and dissolved. The debate became personal, sharpened by questions of credit. Anonymous publication and tone, Galileo's Letters on Sunspots appeared in 1613 under the auspices of the Accademia dei Lincei, and there he expressed Copernican commitment more openly. The Linceian Academy had admitted Galileo during his celebrated visit to Rome in 1611. Founded by the young nobleman Federico Sesi, the Academy took its emblem from the lynx, whose keen sight symbolized the desire to penetrate appearances. It gathered naturalists interested in observation, classification, instruments and correspondence. Its support gave Galileo an intellectual identity beyond court and university. He proudly added the title Lintzen to his name. Sesi acted as patron, editor, mediator, and friend, helping publications through practical and political difficulties. This form of collective support was vital. Because a book emerged from far more than an author's study, permissions had to be secured. Printers managed, illustrations prepared, opponents anticipated, and patrons honored without surrendering the work's substance. Rome in 1611 did not greet Galileo as an enemy. Jesuit astronomers at the Collegio Romano examined his observations and confirmed major telescopic discoveries. Christoph Clavius, elderly and respected, accepted the roughness of the moon and the satellites of Jupiter, though the full cosmological meaning remained open. Galileo was honored at a gathering, met cardinals, and enjoyed a season of extraordinary success. The church contained mathematicians, observers, patrons, administrators, preachers, censors, rivals, and friends, not one single mind reacting in one single way. Some religious scholars supported new astronomy. Some sought compromise, some objected on physical grounds. Some feared scriptural consequences, and some disliked Galileo's manner more than his data. Any truthful account must resist turning this complex institution into a simple wall against which one lonely scientist stood. At the Florentine court, Galileo became involved in disputes that carried the flavor of learned entertainment and serious philosophy at once. One concerned bodies floating in water. Aristotelian opponents emphasized shape in explaining why certain objects remained on the surface. Galileo argued from density and the relation between a body and displaced water. Drawing inspiration from Archimedes, his discourse on bodies in water appeared in 1612. The controversy included public demonstrations, written replies, and social competition. It revealed how experimental scenes could be staged in ways favorable to different interpretations. A thin plate of ebony might float when carefully placed because the water surface was depressed around it, while the same material sank when submerged. Galileo analyzed such cases with impressive insight, though later surface tension would provide a fuller account. Once again, he was neither simply repeating the ancients nor possessing every modern concept. He advanced through a creative mixture of geometry, observation, polemic, and incompleteness. The deeper question was how mathematics could speak about matter. Traditional philosophy often treated mathematics as exact but limited to quantity, while natural philosophy dealt with causes, qualities, and real substances. Galileo increasingly erased that boundary. not by reducing every experience to a number, but by selecting properties that could be measured and related: shape, size, motion, speed, distance, time. He would later write that nature is composed in mathematical language, with characters such as triangles, circles, and other geometrical figures. This famous image did not mean that the universe was a schoolbook already open to effortless reading. The reader needed instruments, imagination, controlled comparison, and the courage to distrust a familiar explanation. His personal life, meanwhile, acquired the quieter rhythms that survive in fragments. His daughters entered the convent at Archetri while still young, taking vows in a community that was poor and often dependent on gifts. Virginia, now Maria Celeste, possessed practical intelligence and deep affection. She prepared remedies, arranged household matters, sent fruit, cakes, collars, and devotional objects. And worried about her father's health, Galileo helped the convent with food, repairs, and influence when he could. Livia, Sister Arcangela, seems to have endured more difficulty and left fewer signs of closeness. Vincenzo, their brother, later studied and married, and Galileo's relationship with Marina Gamba receded from the surviving record. The celebrated observer who mapped lunar shadows also moved within a family landscape of absence, obligation, tenderness, and choices that cannot be made simple. By 1613, the Copernican question crossed more clearly from astronomy into theology. At a meal in the Tuscan court, Galileo's former student Benedetto Castelli, now a mathematician and a Benedictine monk, found himself discussing Earth's motion with members of the ruling family. The Grand Duchess Christina raised scriptural passages that seemed to describe a stationary Earth or a moving sun. Castelli defended the compatibility of Copernican ideas with faith, and when Galileo heard of the exchange, he wrote him a long letter. The letter to Castelli argued that scripture and nature both came from God, and therefore could not truly contradict. But human interpreters might misunderstand one or the other. Biblical language often accommodated ordinary speech and the needs of salvation rather than teaching technical astronomy. Where a physical conclusion had been securely demonstrated, interpreters should seek a reading of Scripture that did not deny it. This approach had roots in respected Christian traditions, including Augustine's warnings against tying faith to claims about nature that reason could disprove. Yet Galileo was entering a sensitive field, for the Reformation and the Catholic response had made authority over biblical interpretation an urgent institutional issue. Copies of the letter circulated. One version was sent to the Inquisition by Niccolo Lorini, a Dominican who criticized the Copernican tendency among Galileo's circle. Historians have studied differences among surviving texts and the question of how wording was altered or defended. But the broader consequence is plain. Galileo's astronomical commitments were now connected to an official examination of doctrine. He expanded his reasoning into the letter to the Grand Duchess Christina, a work of remarkable scriptural argument written by a lay mathematician who believed that theologians should not use biblical passages to settle questions accessible to demonstration and sensory experience. His confidence was bold and perhaps politically unwise, yet it was not an attack on Christianity. Galileo considered himself a Catholic, sought approval within the Church, maintained friendships with clergy, and framed his case as a defense of sound interpretation. He challenged particular decisions and methods of authority while remaining inside the religious world those authorities governed. In the closing months of 1615, Galileo traveled to Rome, determined to prevent a condemnation of Copernicanism and confident that careful argument could persuade powerful men. He spoke in salons, visited cardinals, demonstrated, debated, and wrote with the restless energy of someone who believed that delay might allow weaker reasoning to harden into law. Friends warned that his eagerness could make matters worse, for Rome was not merely an academy where the strongest geometrical proof would carry the day. It was a court, a government, a network of congregations, personal loyalties, doctrinal responsibilities, and memories of recent religious conflict. Galileo knew much about patronage, yet sometimes acted as though clarity alone should command agreement. He could be charming in conversation, but he could also press an opponent until retreat became humiliating. And such victories often produced resentment that survived the evening. The physical evidence for Earth's motion was also less decisive than Galileo believed. The telescope had shown that the old Ptolemaic cosmos could not remain untouched. The phases of Venus demanded that Venus orbit the Sun. The moons of Jupiter showed that there could be more than one center of motion. The rough moon and changing sunspots weakened the idea of perfect immutable heavens, but Tycho's system could absorb much of this evidence while keeping Earth at rest. Galileo thought the ocean tide supplied a direct proof. He imagined that Earth's daily rotation and annual revolution combined to make the seas accelerate and slow within their basins, like water surging in a vessel whose motion changes. The theory was ingenious and deeply mistaken. It predicted primarily one tide per day rather than the ordinary pair, and it discounted the moon's role, which Kepler had connected with tidal action in a way Galileo dismissed as occult. His desire for a mechanical explanation was admirable, yet his chosen mechanism did not fit the full phenomenon. This failure matters because it restores the drama to its proper uncertainty. Galileo was right that Earth moves, but he did not possess a conclusive contemporary proof of that motion, and some of his opponents were wrong for reasons that were not entirely foolish. Cardinal Robert Bellarmine, one of the most influential theologians of the age, responded to the Carmelite Paolo Antonio Foscarini, who had published a defense of Copernicanism and biblical compatibility. Bellarmine distinguished between using a sun-centered system hypothetically to calculate appearances and affirming it as physical truth. If a true demonstration of Earth's motion were produced, he wrote, then interpreters would need to reconsider passages that seemed contrary. But he did not believe such a demonstration had yet been given. The position was cautious, though it also assumed that traditional readings should stand until compelled to change. Galileo wanted greater freedom to pursue the doctrine as real, not merely as a fictional device. Because the physical world revealed by his observations seemed to demand a new philosophy, in February 1616 a group of theological consultants to the Holy Office evaluated two propositions: that the sun stood immobile at the center of the world, and that Earth moved both annually and daily. They judged the first philosophically foolish and formally heretical, and the second philosophically false and at least erroneous in faith. The Congregation of the Index then suspended Copernicus's book until corrections could be made. Later editions carried changes that presented certain claims more hypothetically. Foscarini's work was prohibited, and Galileo was instructed not to maintain the condemned doctrine. The precise form of that instruction would become crucial 17 years later. Surviving records include Bellarmine's report that Galileo was warned and submitted, along with another document stating in stricter language that he must not hold, teach, or defend the view in any way. Historians debate the circumstances and legal status of this injunction because Galileo later produced a certificate from Bellarmine saying that he had not abjured or been punished, but had simply been notified of the declaration and told not to hold or defend the doctrine. For the moment Galileo left Rome without a public conviction of heresy, he had not been tried in 1616, and Bellarmine's certificate protected his reputation against rumors. Yet the boundaries around his future writing had narrowed. He could discuss Copernicanism as a mathematical supposition. He could not openly teach it as established physical truth. This outcome did not silence his mind, but it changed his strategy. He returned to Florence, where health problems, family obligations, court expectations, and intellectual rivalries filled the following years. The prohibition became a quiet line in the landscape, sometimes distant, sometimes close, never entirely absent. Galileo's religious position cannot be captured by imagining that he stood outside faith and confronted belief with reason. He prayed, participated in Catholic life, trusted his daughter's spiritual care, sought ecclesiastical approval, and framed natural investigation as the study of a creation governed by divine order. His dispute concerned authority, interpretation, evidence, and jurisdiction. Who should decide the meaning of a passage when it touched a physical claim? How certain must a demonstration be before interpretation changes? Whether a mathematical model could describe reality, and how an institution under pressure from Protestant challenge should respond when a famous court philosopher publicly entered theology, the conflict would later become a universal symbol of science oppressed by religion. And that symbol contains a real injustice. Because Galileo was ultimately condemned for supporting a true account of Earth's motion, yet the historical scene was more crowded. Some churchmen defended him, some astronomers opposed him, some scientists were clerics, some critics had legitimate evidential questions, and politics shaped the timing and severity of the response. A few years after the 1616 decision, the sky offered another controversy. 3 comets appeared in 1618, attracting attention across Europe. Galileo was ill and did not observe them extensively, but his disciple Mario Guiducci delivered a discourse developed in close consultation with him. Arguing against the interpretation of the Jesuit mathematician Orazio Grassi, Grassi held that comets were distant celestial bodies moving beyond the moon, an idea closer to the later understanding than Galileo's. Galileo suggested instead that they might be optical appearances produced by sunlight and vapor. In this scientific dispute, the man celebrated for telescopic observation defended the weaker physical theory. Yet the controversy became important because of how he wrote about method. Tone and authority, Grassi answered under a pseudonym, and Galileo prepared a larger response, Il Saggiatore, the Assayer, published in 1623 with the help of the Lyncian Academy. The title referred to a delicate balance used to test precious metals, implying that Galileo's analysis was precise while his opponent's reasoning resembled a coarse scale. The book sparkled with wit and contempt, and readers admired its Italian prose. Galileo argued that philosophy is written in the vast book of the universe, always open before our eyes, but impossible to understand unless one learns its language and characters. Mathematics, triangles, circles, and geometrical relations. He also distinguished between properties such as shape, motion, number, and size, which he treated as belonging to bodies, and sensations such as taste, color, odor, and sound, which arise in perceiving creatures through physical interactions. The distinction anticipated later discussions of primary and secondary qualities. Though his account was embedded in the particular theories of matter available to him, the Assayer was dedicated to the new Pope, Urban VIII, formerly Cardinal Maffeo Barberini, whose election in 1623 seemed to Galileo like the arrival of favorable weather after a long restraint. Barberini was a cultivated Tuscan, a poet, a patron of learning, and a man who had shown personal admiration for Galileo. He enjoyed passages of the Assayer read aloud at meals, granted audiences, and spoke with warmth. Galileo visited Rome in 1624 and met the Pope repeatedly. Hoping that the 1616 restriction might be softened, Urban did not revoke the decree, but he allowed discussion of competing world systems so long as Copernicanism was treated hypothetically, and divine omnipotence was not constrained by human arguments. One of Urban's favored points was that God could produce the same observed effects through many causes beyond human knowledge. Therefore, no physical reasoning should claim absolute necessity about the structure chosen by the Creator. Galileo accepted the condition outwardly and began to imagine a book that would compare the Ptolemaic and Copernican arrangements in dialogue. These years carried both promise and warning. The 30 Years' War was spreading devastation through Europe. Confessional alliances, dynastic interests, and military disaster placed enormous strain on Rome's diplomacy. Urban's policies drew criticism from different sides, and the Barberini court grew sensitive to challenges against papal authority. A scientific book could not be separated from this climate, even if its author preferred to speak of tides and sunspots. Meanwhile, plague disrupted travel and printing. Censorship procedures required negotiation between Rome and Florence, and the death of Federico Tesi in 1630 deprived Galileo of one of his wisest patrons and editors. The Lyncian Academy lost momentum, leaving him more exposed at the moment his most ambitious public work approached publication. Before that turning point, Galileo's days moved between intellectual labor and ordinary discomfort. He suffered recurring illnesses, possibly arthritic pain, fevers, digestive problems, and eye strain. He stayed at country houses when Florence's air or court demands became oppressive. He enjoyed wine, gardens, music, and conversation, designed devices for practical uses, advised the Medici, and maintained correspondence across Europe. His social style joined generosity with combativeness. Students remembered his power as a teacher. Friends relied on his judgment. Enemies remembered the cuts in his prose. He could make an opponent's argument sound not merely mistaken, but ridiculous, a gift that delighted allies and complicated reconciliation. The telescope continued to travel beyond his control. Other observers improved instruments, made discoveries, and claimed authority. Maps of the moon became more detailed. Jupiter's satellites were tracked, and the hope arose that their predictable eclipses might solve the problem of longitude. If observers at different places recorded the same celestial event and compared local times, the difference could reveal east-west separation. Galileo developed tables and proposed methods to Spain and later to the Dutch, imagining even a head-mounted device for observing from a ship. But the rolling sea, limited optics, and difficulty of accurate timekeeping made the method impractical aboard vessels. It proved more useful on land for cartography. The episode shows how his astronomy remained connected to navigation, government, and reward. The heavens were not only an arena of philosophy, they could become a clock for mapping Earth. Galileo also explored the nature of motion on a moving Earth through examples that later appeared in the dialogue. Suppose a ship travels smoothly at constant speed, and below-deck fish swim in a bowl. Insects fly, water drips into a container, and a person tosses an object to a companion. No experiment confined within the cabin reveals whether the vessel is still or moving uniformly. All local motions share the ship's overall motion. This principle of relativity answered a common objection to Earth's rotation. A stone dropped from a tower does not fall far to the west because it already shares the eastward movement of the tower and ground. Birds are not left behind because the air and birds participate in the same general motion. The idea loosened the deep intuition that movement must always reveal itself through an internal effect. Only changes of motion, not uniform shared motion, need become evident within the system. His concept remained tied to circular motion in ways later physics would alter. Yet it opened a new understanding of mechanical equivalence. Rest and uniform movement could be relative to a chosen frame. A calm cabin could conceal a voyage, and the moving Earth could feel still. This was one of Galileo's most profound achievements. Quieter than the drama of the telescope, but essential to making Copernicanism physically imaginable. The world beneath one's feet no longer needed to be motionless, simply because no wind rushed endlessly past and no stone landed behind its tower. As he planned the dialogue, Galileo chose a literary form with ancient roots. 3 speakers would converse over 4 days. Salviati would present the strongest arguments for the new science, named after Galileo's deceased Florentine friend Filippo Salviati. Sagredo, named for Gianfrancesco Sagredo, would serve as an intelligent, open-minded gentleman weighing both sides, and Simplicio would defend traditional Aristotelian and Ptolemaic positions. His name belonged to an ancient commentator on Aristotle, but in Italian it could also suggest simplicity. Galileo insisted that the character was not merely a fool, and Simplicio sometimes raises serious objections, yet the structure, rhythm, and accumulated victories clearly favor Salviati. The book would be formally balanced enough to pass as a comparison, while emotionally and intellectually leading readers toward a moving Earth. The first day would challenge the division between corruptible terrestrial matter and perfect celestial substance. The second would consider Earth's daily rotation and the relativity of motion. The third would examine annual revolution and astronomical phenomena. And the fourth would present the tides as the decisive physical argument, unfortunately placing Galileo's weakest major theory at the climax of his masterpiece. The work drew on decades of thought, observation, controversy, and conversation. Its scale was larger than a technical treatise. It offered readers a staged experience of intellectual conversion. Familiar objections were allowed to speak, then gradually surrounded by examples that made the old certainty feel less secure. Galileo wrote not in scholarly Latin alone but in vigorous Italian, widening the audience to educated readers beyond universities. The choice gave his arguments immediacy and helped shape scientific prose. He used towers, ships, horses, bowls, stones, craftsmen, and everyday motions, bringing cosmology down into recognizable life. The dialogue unfolds near the Venetian waters associated with Sagredo, and the imagined setting carries an atmosphere of civilized leisure, intelligent friends talking through long days while the world outside continues. A reader is invited not to receive a decree but to sit among them. Listen, doubt, laugh, and discover. Obtaining permission required care. Galileo initially sought publication in Rome. The papal censor, Niccolo Riccardi, known as Father Monster because of his official title connected with the sacred palace, reviewed the project. Conditions were set. The Copernican theory must remain hypothetical. The opening and conclusion should reflect the Pope's argument about divine omnipotence, and the title should not claim to prove the tides as a result of Earth's motion. Plague restrictions then hindered travel and communication between Tuscany and Rome. Galileo arranged to print in Florence, where local officials and the Inquisitor became involved. Revisions and approvals moved slowly through letters. Some pages were examined in one city and others in another. By the time the book appeared in February 1632, it carried licenses that seemed to place it safely within authorized boundaries. The dialogue was an immediate success. Copies sold quickly. Readers recognized that the supposed neutrality was transparent. Salviati commanded the discussion. Sagredo leaned toward him, and Simplicio repeatedly absorbed defeat. The required argument about God's freedom appeared near the end in Simplicio's mouth, where the surrounding conversation made it seem less like a triumphant safeguard than a final appeal after the physical case had gone against him. Whether Galileo intended to mock Urban personally remains uncertain. He may have believed he had faithfully included the Pope's point, but in the charged atmosphere of Rome, the effect was disastrous. The Pope learned that words he valued had been assigned to the character most often made to look inadequate, and he felt deceived. The book's sale was halted. A special commission examined the approval process, and Galileo was ordered to appear before the Roman Inquisition. He was nearly 70, often ill, and reluctant to undertake the winter journey. The Tuscan authorities offered medical explanations and sought delay, but Rome insisted, and refusing a summons could have brought harsher consequences. So in January 1633, Galileo left Florence, traveling slowly through plague precautions and cold roads. He reached Rome in February and lodged not in a dungeon, but at the residence of the Tuscan ambassador. Later staying in rooms of the Holy Office under comparatively privileged conditions, the courtesy did not make the danger unreal. His freedom, honor, books, family contact, and possibly his physical safety depended on a tribunal whose proceedings were secret and whose authority he could not ignore. The central legal question concerned what he had been told in 1616 and whether the dialogue violated that command. Galileo presented Bellarmine's certificate, which stated that he had not abjured and had been notified not to hold or defend Copernicanism. He argued that the book did not defend the doctrine, but examined arguments and ultimately left the conclusion open. To modern readers and to his judges, this claim strained belief. The work's literary force clearly favored the Copernican side, yet Galileo also confronted the stricter injunction recorded in the file, forbidding him to teach or discuss the theory in any way. He said he did not remember such an order and relied on Bellarmine's certificate. Bellarmine had died, Sisi was gone, and Urban, once a friend, had become the sovereign determined that authority be vindicated. Interrogations took place in April. Galileo answered questions about his intention, the permissions, and the argument of the book. At one stage, he made the extraordinary concession that after rereading the dialogue, he could see that the Copernican side had been presented more strongly than he intended, perhaps through vanity and a desire to show clever arguments. He offered to add material refuting it. The statement was a strategy of survival, not a transparent account of authorship, and the judges did not accept it as sufficient. The trial was never a calm contest in which each side freely pursued evidence. It was an institutional proceeding directed toward confession and submission, but neither was it the dungeon spectacle later imagination sometimes creates. Galileo was not tortured, though a formal threat associated with examination was invoked. He was not blinded by inquisitors, his failing eyesight came later from disease, and he was not burned. The injustice lies in what truly happened, without adding punishments that did not. On the 22nd of June 1633, Galileo was brought to the Dominican convent of Santa Maria sopra Minerva, where the sentence was read. The tribunal declared him vehemently suspected of heresy for having held and defended the motion of earth and the stability of the sun after the doctrine had been judged contrary to Scripture. The dialogue was prohibited, and Galileo was condemned to imprisonment at the pleasure of the Holy Office, with a spiritual penance requiring the weekly recitation of the 7 penitential psalms for 3 years. 7 of the 10 cardinal inquisitors signed the judgment, and Galileo then knelt and recited a formal abjuration, swearing that he rejected and detested the condemned opinions. The words were written for submission, not as a description of his private conviction, and the ceremony marked a public defeat arranged to display the power of the institution over the individual who had crossed its boundary. The famous phrase, "and yet it moves," often imagined as a whisper after the abjuration, does not appear in contemporary evidence. The story emerged much later, and although it expresses the truth that Earth continued moving regardless of a courtroom, it should be heard as legend rather than transcript. The real scene requires no theatrical addition. An elderly man who had spent decades trying to understand motion was compelled to deny the physical arrangement he believed true. His book was banned, his reputation was wounded, and his future movement was restricted. The simplicity of the legend can even conceal the deeper pathos. Because Galileo did not step from the chamber untouched in spirit, he emerged frightened, humiliated, cautious, and still intellectually alive. His formal prison sentence was quickly commuted. First, he stayed under the custody of Archbishop Ascanio Piccolomini in Siena, a cultivated churchman who treated him with kindness. The months in Siena helped restore him after the pressure of trial. He conversed with educated visitors, considered scientific questions, and found an atmosphere less oppressive than he had feared. Piccolomini encouraged his work without openly challenging the judgment, a reminder that even after condemnation, Galileo's world included supportive clergy and nuanced loyalties. By the end of 1633, he was allowed to return to his villa at Arcetri, called Il Gioiello, the Jewel, on hills south of Florence, close to the convent where his daughters lived. There he remained under house arrest for the rest of his life, permitted selected visitors under conditions, forbidden to travel freely, and required to avoid public defense of the condemned cosmology. Arcetri offered beauty and confinement together. Olive trees covered the slopes. Florence lay within view. Bells crossed the air. Vines changed with the seasons, and the sky remained open above a man whose use of the telescope had altered its meaning. The villa was not a cell of stone underground, yet it was a boundary enforced by authority. Galileo needed permission for movement and company. Letters were watched with caution, and publication within Catholic lands became difficult. He was close enough to San Matteo to receive messages and practical help from Maria Celeste, whose surviving letters form the most intimate record of these years. Maria Celeste followed every turn of her father's trouble with tenderness. During the trial she prayed, sought news, and tried to protect him from worry at home. After his return, she took upon herself the weekly penitential psalms, sparing him part of the burden while treating the obligation as spiritual care rather than political judgment. She sent preserved fruit, herbs, bread, linen, and small domestic gifts, advised him about servants and expenses, requested help for the convent, and addressed him with a warmth that dissolves the distance between the famous philosopher and the aging parent. Her letters also reveal the hard conditions of enclosure: illness, limited food, and constant need. Galileo's house might contain books and instruments, yet much of his comfort depended on hands behind convent walls. In April 1634, Maria Celeste died after a sudden illness. She was only 33. Galileo was devastated. He wrote that he felt immense sadness and melancholy, and that life had become hateful to him. The loss arrived less than a year after the trial, when she had been his closest emotional support. The quiet routine of exchanged baskets, remedies, requests, and affectionate words ended, and the villa's nearness to the convent must have deepened the emptiness. History often remembers Galileo through arguments with popes and philosophers, but in our Setri, the death of a daughter may have weighed more heavily than any printed controversy. Even in grief and restriction, he returned to work that had begun long before the telescope: the science of motion and the strength of materials. His final great book gathered investigations developed across decades, placing them within another dialogue among Salviati, Sagredo, and Simplicio. But now the prohibited world systems gave way to two new sciences, one concerning how structures resist breaking, the other concerning local motion, fall, acceleration, and projectiles. The title promised a foundation rather than a final completed physics, and the book's calm demonstrations carried the accumulated force of his early experiments, geometric imagination, and mature style. The first new science examined why beams, ropes, columns, bones, and machines do not preserve the same strength when enlarged. A small model cannot simply be scaled upward without changing the relation between weight and supporting cross-section. Volume grows faster than area, so a giant structure becomes proportionally more burdened by its own mass. Galileo used examples from architecture and living bodies, noting that large animals required different proportions from small ones. The bones of a huge creature must be thicker relative to its size, while tiny organisms can possess delicate forms impossible at a gigantic scale. This insight into scaling linked geometry with engineering and biology, showing that size itself changes what designs are possible. He explored the breaking of cantilevered beams, the resistance of materials, and the behavior of machines. Some details would later be corrected, yet the central recognition endured. Nature does not grant unlimited enlargement through simple imitation. A ship, building, or animal belongs to a scale whose proportions matter. The lesson emerged from practical concerns familiar to craftsmen, but Galileo elevated it into mathematical investigation, joining the workshop and the theorem as he had throughout his life. The second new science presented his account of uniformly accelerated motion. When a body falls from rest, its speed increases in a regular way, and the distance covered grows with the square of elapsed time. Galileo expressed results through geometrical ratios rather than the algebraic notation now familiar. He considered motion along inclined planes, horizontal projection, and descent, then combined uniform horizontal movement with vertical acceleration to show that a projectile follows a parabolic path under ideal conditions. Cannonballs in the real world encounter air resistance and other complications, but the ideal parabola revealed the underlying structure. The same mathematics could describe a stone rolling from a table and an artillery shot crossing open ground. Celestial wonder and military practice belong to one searchable nature. He also returned to pendulums, chord lengths, musical consonants, and the relation between motion and measure. The book unfolded as a conversation over days, allowing objections to arise and demonstrations to breathe. Readers encountered not a list of laws, but the architecture of inquiry. Familiar experience was converted into diagrams, apparent contradictions were used as entrances, and ideal cases clarified the noisy world. Galileo could no longer roam freely. But within the page he moved across slopes, towers, beams, trajectories, and imagined laboratories with greater reach than before. Publishing the work required bypassing the controls that surrounded him. The manuscript left Italy and reached the Dutch printing house of the Elsevier family in Leiden, where discourses and mathematical demonstrations relating to two new sciences appeared in 1638. Galileo stated that the text had come into foreign hands without his initiative, a protective fiction that allowed distance from the forbidden act of publication. Europe received the book while its author sat under restriction, and younger thinkers recognized it as a treasury of problems and methods. The work secured a legacy deeper than the telescope alone, for it helped establish the mathematical study of motion that later passed through Descartes, Huygens, Newton, and many others. By the time the book appeared, Galileo had lost his sight. First one eye failed, then the other, likely through cataracts and other disease. Blindness carried a cruel symbolism that later writers could hardly resist. The man who had shown new worlds could no longer see the faces of visitors or the sky above Archetri, yet he continued to dictate, reason, listen, and converse. Sight had been central to his fame, but his science had never depended on sight alone. It required memory, geometry, touch, rhythm, language, and the ability to move through an imagined construction. In darkness, he could still follow a ratio, hear an argument, and recognize whether a conclusion followed. Among those who visited and assisted him were the young Vincenzo Viviani, who became a devoted pupil and later an important guardian of Galileo's memory, and Evangelista Torricelli, whose work on fluids and pressure would lead toward the barometer. Their presence connected the aging philosopher to a generation that would carry experimental mathematics into new forms. Conversations at the villa became a bridge, ideas passing from a man born when Renaissance courts still looked backward to antiquity towards students entering the age of academies, precision instruments, and increasingly international science. Galileo considered designs for a pendulum clock and continued discussing longitude, lunar motion, and mechanics. His mind did not close after the trial. Though his freedom of expression remained constrained, he was granted permission at times for limited visits or medical arrangements, but attempts to move permanently were resisted. Friends abroad sent news, books, and admiration, while Catholic censorship reduced the circulation of his condemned cosmological work in some regions. The boundary around his body could not contain the network of readers who studied his pages. On the 8th of January 1642, Galileo died at Arcetri after fever and heart trouble. He was 77. Attendants, family, and pupils marked the end of a life that had stretched from the lute music of Vincenzo's household to the first telescopic transformation of astronomy. The Grand Duke wished to honor him with an imposing tomb in the Basilica of Santa Croce, beside other distinguished Florentines, but papal opposition prevented the immediate monument. Because a public celebration of a man condemned by the Inquisition seemed inappropriate, he was buried in a modest place within the church complex. His remains would not be moved to the prominent tomb now associated with him until 1737. It is often said that Isaac Newton was born in the same year Galileo died. A symbolic passing of light from one great physicist to another, the statement depends on calendars. Galileo died in January 1642 according to the Gregorian calendar used in Tuscany, while Newton was born on Christmas Day 1642 according to the Julian calendar then used in England, corresponding to January 1643 in the Gregorian reckoning. The coincidence remains close enough to inspire reflection, but history needs no perfect relay. Newton inherited not a single torch from a single predecessor, but a broad field shaped by Galileo, Kepler, Descartes, Huygens, Wallace, and many others. His laws of motion and universal gravitation would join terrestrial fall with planetary orbit in a synthesis Galileo had helped make conceivable. Even though Galileo himself resisted Kepler's ellipses and never possessed Newton's concept of gravity, the immediate judgment against Galileo did not stop astronomy from moving toward heliocentrism. improved observations, Keplerian prediction. Newtonian mechanics and the later detection of stellar effects gradually supplied forms of evidence unavailable in 1616. Catholic scholars continued to work in astronomy, sometimes navigating restrictions through cautious language, and the institutional response changed slowly rather than through one dramatic reversal. Editions of heliocentric works remained entangled with censorship for generations, then permissions broadened. In 1757, the general prohibition on books teaching Earth's motion was removed from the index. In the early 19th century, official publication of openly heliocentric works was allowed, and in 1992, Pope John Paul II publicly acknowledged errors made by church authorities in the Galileo case after a commission had studied its history. That later acknowledgement did not erase the sentence, nor did it settle every argument about motives, procedure, and responsibility. Historical interpretation continues because the affair contains many layers: scientific evidence, biblical interpretation, personal rivalry, court politics, censorship, papal authority, legal ambiguity, literary provocation, and the difficulty institutions face when admitting uncertainty. Calling it merely a war between science and religion removes the religious people who supported Galileo and the scientific weaknesses within his own case, yet calling it only a misunderstanding would minimize coercion and injustice. Galileo was compelled to abjure a position that was fundamentally true. His book was suppressed, and an authoritative institution treated controlled interpretation as more important than open inquiry. The mature understanding holds complexity without dissolving the moral fact. The story of Galileo became larger after his death because each age discovered a figure suited to its own concerns. Enlightenment writers saw a champion of reason against dogma. 19th century authors sharpened the conflict into a dramatic struggle between science and faith. Political reformers used his trial as evidence against clerical power. Defenders of the Church answered by emphasizing the limits of his proof and the support he once received from clergy. Modern historians opened archives, compared documents, reconstructed patronage, and showed that none of the simplest versions can contain the whole life. Yet the continued debate is itself a measure of his importance. Galileo stands where observation, mathematics, rhetoric, technology, religion, and government meet. And every attempt to isolate one of those elements leaves something essential outside. Several familiar legends gather around him like bright stars that appear close together from Earth, while lying at very different distances. The swinging cathedral lamp may preserve a truthful memory of his interest in pendulums without proving the exact scene. The balls dropped from the leaning tower may reflect demonstrations or later testimony without offering a secure contemporary spectacle. The whisper that Earth still moves expresses defiance, but belongs to a later tradition. The claim that he invented the telescope ignores the Dutch origin of the spyglass, while overlooking the genuine brilliance with which he improved and transformed it. The title father of modern science honors his influence but can hide predecessors. Collaborators, rivals, artisans, and successors. Removing the legends does not make him smaller. It reveals a more impressive achievement. He worked within uncertainty and limitation, with imperfect glass, incomplete mathematics, unstable patronage, incorrect ideas, bodily pain, family need, and dangerous authority. And from that human situation, he changed the questions that could be asked. His deepest contribution may not be any single discovery, but a new alliance among ways of knowing that had often remained separated. Geometry offered ideal relations. Experiment created manageable events. Instruments extended perception, craft supplied devices. Writing persuaded communities, and criticism forced claims into sharper form. Galileo did not invent each part. Greek mathematicians, medieval natural philosophers, Renaissance engineers, Islamic astronomers, lens makers, navigators, artists, and many others had prepared the ground. His originality lay in the intensity with which he brought these resources together and made them public through unforgettable arguments. Consider the moon again. Before the telescope, it could be discussed through naked eye appearances, philosophical categories, and inherited cosmology. After Galileo, a rough boundary of light became measurable terrain. The shadow of a peak became evidence of height, and a drawing trained by perspective became part of astronomy. Consider Jupiter. 4. Faint points became bodies because their repeated changes formed a pattern over time. Observation was not one glance, but a sequence, a diary, a comparison. A disciplined return on another night. Consider falling bodies. The event happened too quickly for easy timing. So the problem was altered. A slope slowed the descent. Water measured duration, geometry joined intervals, and an ideal law emerged from a designed arrangement. In each case, nature did not simply announce an answer. Galileo built a path along which the answer could become visible. He was also a master of intellectual theatre. The tower, ship, bowl, cannon, pendulum, and moving cabin allowed readers to perform experiments in imagination. Even those who never touched his instruments could follow the scene. The method of thought experiment did not replace physical trial. It exposed consequences and contradictions that ordinary perception concealed. Tie a light stone to a heavy one, smooth away friction, lengthen a slope, close the cabin of a ship, enlarge an animal, and the mind reaches conditions that no workshop can perfectly produce. Later, science would depend heavily on this movement between the actual and the ideal. His errors deserve a place in the calm final judgment because they belong to the same creative mind as his successes. He rejected Kepler's elliptical orbits, offered a mistaken theory of comets, insisted too strongly that tides proved Earth's motion, underestimated lunar influence, and sometimes treated rhetorical victory as if it were demonstration. He could be unfair to opponents and slow to credit insights that did not fit his preferred mechanical picture. These failures do not cancel his work. They show why science cannot rest upon genius alone. Even a powerful observer needs criticism, replication, alternative models, and later correction. The durable method is larger than the person who helped shape it. The church officials who judged him also inhabited a world more complicated than caricature. Astronomy served the calendar. Jesuit mathematicians made respected observations. Universities supported natural philosophy. And educated clergy could admire Galileo's telescope while questioning his cosmology. Bellarmine's request for demonstration was not in itself hostile to reason. Yet the institutional decision of 1616 transformed a disputed physical claim into a doctrinal boundary, and the trial of 1633 enforced that boundary through coercion. Once authority made a scientific model answerable to a fixed interpretation of Scripture, the space for correction narrowed. The tragedy was not that faith and inquiry must always be enemies, but that people with the power to compel submission refused to leave a difficult natural question open. Galileo's own biblical writing offered a path that later believers and scientists could recognize. Sacred texts speak to human salvation through languages, genres and images suited to their audiences, while nature follows an order accessible through observation and reason. Apparent conflict may arise from interpretation rather than from creation itself. He did not invent this principle from nothing, but he applied it boldly to the new astronomy. His confidence crossed institutional limits, yet the underlying insight survived the judgment against him. His literary legacy remains as important as his instruments. The dialogue and the assayer turned technical controversy into living prose. Instead of burying motion under scholastic vocabulary, he filled pages with voices, gestures, familiar objects, and impatient intelligence, Italian readers could feel thought unfolding. Objections were not hidden, but dramatized, and the reader became a silent fourth participant. This style helped science enter public culture. It also increased danger because a vivid argument can wound authority more deeply than a cautious table of numbers. The quietest part of his legacy lives in measurements repeated by people who never invoke his name. Every classroom demonstration of inclined motion, every discussion of frames of reference, every diagram of projectile paths, every telescope turned toward Jupiter's 4 large moons, and every engineering calculation that respects the effects of scale carries something of the world he helped form. The European navigation system named Galileo Spacecraft visiting Jupiter, lunar maps, precision clocks, and observatories on distant mountains belong to technologies he could not have imagined in detail. Yet their confidence that hidden motions can be revealed through mathematics and instruments would have felt familiar to him. Return now in imagination to our Khetri, not on the day of trial or death, but on an ordinary evening in the final years. The hills cool after sunlight, leaves settle, servants complete their tasks, a visitor lowers his voice, and the blind old philosopher sits among remembered diagrams. He cannot see Venus becoming a crescent, cannot watch a moon emerge from Jupiter's shadow, cannot trace a sunspot across the projected disk. Yet the motions remain within him as relations. A falling body gathers speed. A projectile bends from a straight intention into a curve. A pendulum divides time. A beam carries its burden until proportion fails. The universe has not become simple, but it has become more measurable. Perhaps Viviani reads a passage aloud. Perhaps Torricelli asks about water and weight. Perhaps Galileo recalls the open rooms of Padua. The view from the Venetian bell tower, the first uncertain points beside Jupiter, the crowded Roman honours of 1611, the tense chamber of 1633, the baskets once sent from Maria Celeste, and the book travelling beyond Italy without him. A life does not arrange itself into neat chapters while it is being lived. Hope and error, ambition and affection, courage and calculation remain mixed. Only later do storytellers draw a single line through the years. That line is often described as challenge. The scientist who challenged the church, and there is truth in the phrase. Galileo resisted efforts to confine astronomy within inherited interpretation, defended the reality of a moving Earth, and continued writing after warning. But he also sought the church's approval, welcomed clerical support, believed himself a faithful Catholic, and hoped that authority would adapt to demonstration. His challenge came from inside a shared world, which made the rupture more painful. He did not approach Rome as a stranger announcing the end of religion. He approached as a celebrated philosopher asking a powerful institution to distinguish eternal faith from a changeable cosmology. The lesson is therefore gentler and more demanding than the legend of one brave man against universal darkness. Evidence may arrive through fragile instruments and still deserve attention. Institutions can contain brilliant individuals and still make grave collective errors. A correct conclusion may be defended with an incorrect proof. An opponent may raise a reasonable question while supporting the wrong model. Language can open minds and provoke pride. Friendship can become danger when politics changes. And truth does not guarantee safety for the person who speaks it. Science after Galileo learned to build protections against some of these weaknesses: publication, replication, mathematical clarity, shared standards, independent criticism, and communities extending beyond a single court or nation. None of those protections is perfect, and modern institutions can also reward conformity or punish unwelcome findings. But the Galilean story reminds us why questions must remain answerable to evidence, why authority should not decide the motion of planets, and why certainty must be proportioned to what has truly been shown. As the night deepens, picture the telescope itself resting on a wooden table, a narrow tube, simple beside modern observatories, its lenses dim, its surface warmed by hands. The object contains no automatic revelation. Without careful alignment, it shows confusion. Without repeated watching, it offers no orbit. Without a mind prepared by geometry, its lights remain lights. Galileo's greatness was not that the tube spoke only to him, but that he taught others how a new sight could become public knowledge. Critics looked, Jesuits confirmed, Kepler praised, rivals repeated, and the heavens gradually ceased to belong to unaided vision alone. Picture also the pages of the dialogue closed after a long day of conversation. Salviati's confidence, Sagredo's curiosity, and Simplicio's resistance all silent together. The book was banned, yet its questions moved across borders. Censorship slowed circulation but could not restore the old sky. Once mountains had appeared on the Moon and satellites around Jupiter, readers could not unknow them. Authority could govern bodies, licenses, appointments, and presses, but observations repeated elsewhere acquired a freedom no decree could fully contain. The title Starry Messenger carries a final peaceful image. Galileo announced himself as the bearer of news from the sky, but the message was not delivered once and completed. Every generation receives another version. Worlds circle other stars, galaxies gather beyond the Milky Way, space-time bends, planets form from disks, and light brings histories across immense distance. Modern knowledge has surpassed Galileo so completely that much of his cosmos now seems small. Yet the habit of listening to unexpected evidence remains close to his first winter nights. He did not prove that humanity was insignificant, as some later summaries suggest, nor did heliocentrism merely push people from a privileged center into emptiness. His work revealed a universe richer in places and motions. The Moon became terrain, Jupiter became the center of a family, the Milky Way became innumerable suns, Earth became a traveler, and human intelligence gained a broader home through understanding. Losing the center could also mean joining the cosmos. The bells of Pisa, Florence, Padua, Venice, Rome, Siena, and Arcetri belonged to different stages of his life. Each city gave him something and took something away. Pisa gave birth, study, and first teaching. Florence gave art, family duty, Medici patronage, and later restriction. Padua gave freedom, friendship, instruments, children, and productive years. Venice gave glass, publication, and the public telescope. Rome gave triumph, warning, and judgment. Siena gave a brief refuge after humiliation. Arcetri gave grief, darkness, final work, and death. Across these places, the story moves like a long orbit, returning to questions first formed in youth while never occupying the same point twice. Now allow the dates and disputes to recede, the consultants of 1616, the censors of 1632, the cardinals of 1633, the printers of Leiden, the later commissions. Let them fade into the distance without being forgotten. What remains is an old human act. Someone looks carefully at what others have seen many times, notices that the appearance does not fit the accepted account, and chooses to look again. The second look becomes a record. The record becomes a pattern. The pattern becomes a question placed before the world. Galileo's life did not end with complete victory. He died condemned, his daughter was gone, his eyes were dark, and the grand tomb planned for him was denied. Yet the motions he studied continued. Earth turned through the January night. Jupiter's moons crossed their paths. Projectiles curved, pendulums swung, and beams carried their weight. Nature did not need the sentence to be reversed before obeying its own order. Centuries later, the reversal came slowly in human institutions, while the sky had never paused. And so the entire story settles not into a shout of defiance, but into a patient confidence. Observation may be delayed, misunderstood, politicized, or forbidden, yet careful knowledge can survive through notebooks, students, instruments, copies, and conversations. One person's courage matters, though no discovery belongs to one person alone. Authority matters, though it must remain capable of correction. Imagination matters, though it must return to evidence. And humility matters, because even the man who helped Earth move in the human mind could be wrong about comets, tides, and circles. Rest now beside this long history. Beneath the same broad night that once opened above a Tuscan telescope, the Moon carries its mountains whether watched or unseen. Jupiter keeps its quiet companions. Earth turns without sensation beneath sleeping houses. And the old philosopher's questions drift far beyond the walls that confined him. Not as restless arguments now, but as gentle reminders that the universe is always larger than a settled answer. That knowledge begins with attention, that truth may require time, and that even in darkness the mind can continue to move.